Welcome. In this video I'm going to show you how you can perform a Brunner Munzel test with Python. I'm running Jupyter Lab with Python version 3.12. This video will focus on how to obtain the output, not so much if you should be using this test and how to interpret it. To show you an example, I'll load in some data. So I'll first import pandas, so then I can use its read CSV function to load in some survey data among students. I actually don't need all of its data, I just need one ordinal field. So I'm going to be using mixed number of activities, which as you can see was ordinal. However, it's text, so I'll also be using coding to say, well, this is the first category, this is the second, etc. as a dictionary. To see the nominal variable, which hopefully only has two in this case, indeed only male and female were selected, so it's actually a binary variable. In a separate video I'll show you how you can simply use my own function to do this test, but in this video I'll show you how to do it with SciPy or stats models, or the hard way without, or almost without libraries. So SciPy has a Brunner Munzel function, but it requires the two categories to be split. So that's what I'm doing over here. And then I could try to use it immediately, but then I get an error, as you can see, because that's still only text. So we can actually use that coding to replace the values and make sure they're ordered. It then will actually work, but somehow it's doing something strange because it's not really numerical yet. So what I did was I used the category codes to actually make them numerical. And then we get the same result as you would see with my own function, a test statistic of -4.5 and a p-value far below the 0.05 usual threshold, because this means that we should divide this by 10 to the power of 5. Now it's not reporting back the degrees of freedom, which it probably should, but there is also in stats models, there's a function called rank compare to independent, and that actually also does a Brunner Munzel test. It gives a lot of output, but the test it's using, as you can see, is actually also a Brunner Munzel test. The degrees of freedom are now actually shown, and the p-value is also shown. Oh, this is actually still using the scat. It should be using the numerical cat. That's why the results didn't look the same. Now they should, and indeed now they do. We can see the same result as with the previous with SciPy, but we also get the degrees of freedom. If you don't want to use any libraries, yeah, then it becomes a little bit more tricky. So I'll assume you actually just have numeric scores to begin with. So here I'm actually making ordinal scores using a mapping and then the coding. I separate the male and the female ones, remove any missing values with drop NA, and make sure they're all a list. So now I have two lists, one for each category, both with just numbers, and a full list where they're all combined. The sample sizes can easily be found now. We simply use the len function, and then we need to actually create some ranks. Now, if you're not want to use any other library, that's a little bit tricky. So I wrote a small function that can calculate or determine mid-ranks. Let's define and use that function. So I want a mid-ranks of all the variables. The mid-ranks if I only use the first category, the mid-ranks of the scores of only the second category. We actually need also the average of the mean of the combined ranks for each category. So the average of these ranks for each category. So for the first category, that's the zeroth index till n1, up to but excluding n1. The sum of those divided by n1. And for R2 it starts at n1 and ends with the last one, and then divide of course by n2. We need the difference between the overall mid-rank, that's this one, and the within mid-rank. So those are known as placement values, so we can use some list or for loop comprehension for that and get those two for each of the two categories. Then we determine the mean for each of these. And then finally we can calculate the variance of those depending on which category. So again, I'm going to sum, that's what this one does, the value itself minus the corresponding average, that this part, raised to the power of 2. And we do that for all of them, so for I in the range of n1 and the other one for the range in n2. Then the estimated variance is the previous result divided over the grand total minus the corresponding column squared. So that gives us these two values. And then the total of that is you sum those two, you divide each by the corresponding sample size, sum the result of that, and multiply with the grand total. Alright, the test statistic is then the difference between the average of the mid-ranks divided by the square root of the sample size times and then the result we just saw. Now, taking a square root can be accomplished by taking something to the power of a half, and that gives us a test statistic of a minus 4.47 if you round. There's an alternative way to actually obtain this. You can use this formula. And then calculate the test statistic using this one. And as you will see, that actually gives the exact same result. Now, they say if Brunner and Munzel suggest if n1 and n2 are large enough, you can use a normal distribution approximation. Otherwise, you can use a t-distribution with this number of degrees of freedom. That looks scary, but we actually have everything for this, so it's just a matter of filling out the formula. You can also rewrite it simpler like this, and that should give us the same result. Now for the t-distribution itself, that's where you probably want to use a library from SciPy, for example. And then you might as well use their function, but okay. I do have a separate notebook if you're interested on how to do a t-distribution without libraries, but I'm going to be using SciPy stats for this, and then their cumulative density function, and that gives us that final p-value. Or if it was large enough, you can use the normal distribution approach. If you're really interested, I'll leave a link to this file on my website. But I also have the studentized permutation test where you just go over all the steps. This was the original one. And then you actually go over all the possible permutations, or at least a lot of them. And keep track of how many are above or below the observed result. You can then actually calculate an expected probability. In this case, that's 0.0074. Alright, I hope this video was helpful, and thank you for watching.